All right, welcome again, students, to Chemistry with Mr. Rogers. And today we're going to begin a new section, a new chapter. This would be Chapter 8, and this will deal with actually quite a few different things, including naming is going to be probably the largest part of this section, how to name compounds. And that's going to start with what are kind of the prelude to that is what are called oxidation numbers, and we're going to learn their rules. Now, you're not actually going to have to memorize all of the rules, and it's not that you're going to have to list them on a test, but you are going to have to be able to know how to use them, and that's the important thing. So we're going to start with going over what are oxidation numbers, and then we'll kind of deal with what are the basic rules. And today we're only going to cover the first three rules, and these are not in any particular order. So it's not like rule number one has to be rule number one. It's just these are kind of the first three listed in your book, and we'll work from there. So first of all, let's answer the question, what are oxidation numbers? Basically, their purpose is they're used to describe the movement of electrons between atoms. Last chapter, we talked a lot about chemical bonding, and we saw how electrons can move between atoms in an ionic bond, how they can be transferred away from the metal to the non-metal. And as a result, you get ions created from that. In a covalent bond, we saw how those atoms are shared, but a lot of times you end up with what we call a polar bond. So the electrons are shifting towards one atom or the other. And that's where oxidation numbers come in. And ultimately, we'll use these to help us with the naming process. But right now, we just want to kind of get a grasp on what they are. So we're going to start there. Positive oxidation numbers mean electrons have moved away from the atom. And so that's kind of a key thing to understand, is what do the positive and negatives mean. If you have a number, or an oxidation number of a particular element or atom, and it's positive, it means that the electrons have moved away. And this would be like in an ionic bond, and you have a metal that's lost electrons, that would be the situation there. Or if you have a covalent bond, and it's a polar bond, and the electrons shift away from that particular atom, then you have, like, let's say, chlorine and hydrogen are bonded together, and the electrons shift away from hydrogen towards chlorine, then hydrogen would end up having a positive oxidation number because the electrons have moved away. A negative oxidation number means the exact opposite. It means electrons have moved towards the atoms. So like in an ionic bond, this would be the nonmetals as they gain electrons. In a covalent bond, this would be the more electronegative element that is pulling the electrons towards itself. So that's basically what positive and negative oxidation numbers mean. And basically, scientists have developed some basic rules for assigning oxidation numbers to predict how an element will combine with other elements. And this comes into the naming procedure in terms of how do I know that you have, let's say, 2 iron atoms bond with 3 oxygen atoms. Or how do I know it's not 1 iron atom bonding with 1 oxygen atom? There are some basic rules and guidelines that will help me figure that out. So I know exactly how many are bonding with what. And that we'll get into a little bit later this chapter. We're going to start with just going over some of the rules. Rule number 1, and what we're going to do actually as we go through these rules, I'm just going to basically state them, and then we'll kind of draw them out so you can kind of visually see what's going on and what do we mean by this, and then we'll do a lot more practice in class. So to start with, rule number 1, this is one that you really are not going to deal with a whole lot because there's not a lot of elements that are free. And this says that the oxidation number of atoms in their natural form or in their pure element is always equal to 0. And this will be very rare. A natural form means before they bond. And we said that most atoms bond with the exception of the noble gases because they're at high energy states, they're unstable, so they go through that process of bonding, whether it's ionically or covalent bonding. And so normally you're not going to find atoms in their natural form, so that's pretty rare. Pure elements you sometimes find, like oxygen bonded with itself in those situations. So if you have an atom all by itself and it's not an ion, it hasn't gained or lost electrons, or it's bonded to itself, in that case you won't have any shifting of electrons yet because it hasn't bonded. Or if it has bonded to itself, then it's a non-polar bond, so there's no shifting of electrons. So we say that the oxidation number is 0 because there's no movement of electrons. Remember, oxidation numbers are meant to describe the movement of electrons. So there's 0 movement. So that's rule 1. And again, rule 1, very rarely you're going to have to use that one because most atoms are bonded. Rule 2, you are going to use a lot more frequently, and this is the ion rule. And basically it says that the oxidation number of an ion is equal to the charge of the ion. So and this is going to apply more to ionic bonds. So if you have an ionic bond, let's say you have something like calcium, and it has 2 valence electrons, it loses those 2 valence electrons, it becomes an ion, it's positive 2. Well, if I know that it lost 2 valence electrons and its charge is positive 2, then that's what its oxidation number is as well. And again, that makes sense because I'm describing the movement of electrons. And like we said before, positive oxidation numbers tell us that electrons are shifting away. And so if my metal is losing electrons, I'm going to have a positive oxidation number. And for each electron that I lose, I'm going to have an oxidation number. So 1 for 1 electron, 2 for 2 electrons. So I get a positive 2 to tell me that I've lost 2 electrons, or that 2 electrons have moved away. And the reverse would apply if you had, like, say, a non-metal that's gaining electrons. So if I had something like chlorine that's gaining 1 electron and it ends up with a -1 charge, then its oxidation number will be -1. Very simple. Rule number 3 will probably be your best friend. This, if you know and can't remember any other rule, this is the one you really, really need to memorize and understand how to use. And it's called the zero-sum rule, and it basically is real simple. It says that the sum of the oxidation numbers of all the atoms in a compound must be 0, or have to equal 0, maybe is a better way to word that. And basically what this allows us to do is we can set up the entire compound in an equation, basically, where I can figure out, well, what if I know let's say I have 2 elements in a compound and I know the oxidation number of one of them, how do I find the oxidation number of the other one? I can use kind of an algebraic equation, where make the unknown x, and I know the whole thing has to be equal to 0, and then solve for it. And I'll show you how that works. And this will actually help you find a lot of oxidation numbers that you may not know initially. So this will actually be your best friend. All right, here I've got some examples drawn, and we're kind of make reference back to some of the things that we did earlier down here. Actually, oops, let me back up on that here. If I can draw on these here. Yeah, here we go. I'm going to take a look at these. Let's see, the first one there you see is magnesium, and then you have O2. So that first line there, we're going to have magnesium. And magnesium, you'll notice here, is all by itself. And if we had one that's all by itself here, like this one here, or you had oxygen, which is an element bonded to itself, this would be the free element or pure substance rule. So this would be rule number 1. And this would be a situation where magnesium is not an ion. You notice it has no charge. And so in this situation, what we would say is because the electrons have not moved, then we would say the oxidation number is 0. Over here, you'll notice that you have oxygen bonded to itself. And so here's your double bond between the oxygens. Because you have oxygen on either side of the bond, it's a nonpolar bond, so it's an equal tug on that bond. So as a result, well, what's the oxidation number of oxygen? It's going to again be 0 because there's 0 movement of electrons. So that's what we mean by an element that's by itself, that has no charge. Okay, in this situation, if we look down below it, if you see NaCl here, so we'll look at this one, and then over here the magnesium fluoride, so those two. What we're talking about on these here is these are ionic bonds, which tells us that these are ions. So rule number 2 would apply here. And so I look at sodium, and I see that sodium is a metal, and metals are going to lose electrons. So I realize, oh, sodium, it loses 1 valence electron. It has a charge of +1. And so if it has a charge of +1, then that has to be its oxidation number as well. The charge and the oxidation number are the same thing. So if I want to know what it is, if I know it's an ionic bond, then all I need to figure out is its charge. And you guys should already know how to figure out the charge. Chlorine here, again, this is an ionic bond, sodium and chlorine. Chlorine is going to gain one valence electron. When it does, because it's an ionic bond, it's going to have a charge, and in this case its charge is going to be -1. And so as a result, that's also its oxidation number. Whatever its charge is, that will be its oxidation number. Now that only works for ionic bonds. Obviously a covalent bond, they don't have charges in the same sense, and so as a result we can't find an oxidation number of a compound or an element using that with a covalent bond, and we'll kind of deal with covalent bonds a little bit later. Right now we're going to work with kind of ionic bonds, since that's the second rule. And then magnesium over here, magnesium has 2 valence electrons, so it's going to lose those 2 because it's a metal, and that makes it a +2 charge, and because it has a +2 charge, then you end up with a +2 for its oxidation number. Fluorine is a halogen. It only needs 1, so it's going to have a charge of -1, and so its oxidation number is going to be -1. So that's how that works, basically. And now we're going to go on to this one, and our third rule kind of puts all these things together. And again, we're going to stick with ionic bonds here, so we're going to start with that. You have potassium and sulfur together, and the third rule basically stated that, well, the sum of all the oxidation numbers has to equal 0. And so this first one, I just want to check and see if that's true. Well, I have an ionic bond here. Potassium, I know, has 1 valence electron. It's going to lose that 1 valence electron, which makes its charge 1. And so I know that it's +1. You'll notice there's 2 here. So I can kind of, well, actually, let me do sulfur first. Sulfur gains 2, so its charge is -2, which means its oxidation number is -2. And if I want to see the whole thing, we said has to equal 0. So if I want to check and see, does it actually equal 0, I can figure this out. I have potassiums, I have 2 of them, and they each have a value of 1. So I can put a little parentheses there. Plus, because remember it's sum of all the oxidation numbers. And then over here I had a -2 for sulfur. And sure enough, if I do the math there, that equals 0. Okay. Now what if I have, this rule comes in real handy, is if I have a situation where I don't know one of them. So for example, here I know chlorine. Chlorine is -1. It needs to gain 1 valence electron. But I don't know iron. I don't know how many valence electrons iron has off the top of my head. And so what I do is I'm going to set it equal to 0 because I know the sum of all these has to equal 0. I don't know what iron is, so I'm going to put an X here. Algebraic formula. I don't know what it is. And since I've only got 1 iron, it's just regular X. If there were 2 irons, it'd be 2X or something like that. Plus, and then I have 3 chlorines, and each chlorine is a -1. And then you've got your basic algebraic equation. And you guys should all know how to solve this. 3 times -1 is -3. I'm going to add that to the other side to figure out what X is. And when I figure that out, X would be equal to 3. And so what's my oxidation number of iron? It's 3. Okay, so that's how I would go about working it. What I'd like you guys to try is, if you need to go back and listen a little bit how I would set this up and figure this out, I'd like you to try this third one here with titanium and phosphorus. It is an ionic bond. You should know what the charge of phosphorus is, and then figure out, well, if I know the charge of phosphorus, how would I find titanium? And we'll check in class and see if you've got it correct.